Well, welcome to Pycon Ireland. I thank the organizers for inviting me. This is my third time visiting Ireland. Beautiful and kind of uniquely habitable country. Whenever I'm here, it just occurs to me, except for this visit, like how little deadly weather you have. I mean, I live somewhere where it's both very uncomfortably hot in the summer and you can freeze to death easily in the winter. And Ireland is just very tranquil, and I know it gets chilly in the autumn and winter, and little on the side of warm in the summer, but really seems uniquely habitable. If we had to ever scale back as a species, I think this would be a good place to set up shop. It just seems to have a lot fewer snakes than most other parts of the world. Here in my talk this morning, I would like to just think about what the emotions of programming are like. I know that in a programming community, especially it's using a language like Python, that at the moment is getting so much attention from novices, so many attention from people that aren't natively computer programmers, but are just getting started. We often are meeting people, running into people in our meetups that are just getting started. And I want to talk about what it feels like to try to program, to try to be creative, to try to create something, and the way that those emotions might be novel or even difficult for people new to that process. So I'll start by talking about patterns. Existing solutions that you recognize and that you've seen before turn up everywhere. Unfortunately, patterns in computing very often bring to mind the Gang of Four book from the 90s, design patterns in object-oriented software, and people think of patterns as merely a way to undo the shackles of C++ so that it's a little more flexible like Python. But really, patterns are a universal way of going through your day, whether you're a farmer, a construction worker, or a computer programmer, and getting things done in an orderly and efficient manner without having to reinvent all of the wheels that you're using or dealing with. So to give some other examples of the way that we pattern match in order to solve problems, I remember when social media was invented. I was used to blogs and blogs. When I saw a blog article in a stream of articles that I wanted to share, it was quite simple. The title of the blog article was always a link to a single page dedicated to that single article by itself, because you quickly learned if you sent your friend a link to the blog, by the time they got to it, the article you wanted to show them would have scrolled off. So you could click on the title and get a permalink that you could send your friend that would always get them to that article. And then they invented social media that didn't have titles. Facebook posts don't have a title. Tweets, no title. Instagram, no title. It was months until I happened one day by accident to click on the date. The date and time next to a social media post is the link to the post. I thought it would be like a link to that day or something. Like you would go visit October 19th on the web. But no, the original social media designer decided that the date would be how you linked to the thing itself. And once you learn that, the world is unlocked. Once you know that design pattern they're using, you now know how to get the link to all social media. Text fields in your browser on the web. It was years before I ran across the fact they have their own do and undo buffer. I always knew that in a big spreadsheet or a text editor that Control-Z would undo what I had just typed and Control-Y would put it back if I decided I'd wanted it. It turns out, one day I just accidentally hit Control-Z in this little text field, and it undid what I had just typed. It had never occurred to me that a miniature little text field would be its own little realm of do and undo. I now can fix it when I click on a link to edit it in the top bar of my browser, accidentally hit backspace, and it's all gone. I just grin wryly at my browser, hit Control-Z, and it comes right back. Actually, hitting Escape, I learned one day by accident, also brings it back. That's a pattern that has saved me lots of time. It was embarrassingly enough, it was at the beginning of this year that I sat down to get ready for a backpacking trip. A friend of mine's gotten me back into backpacking after years away, and these days you try to do ultralight backpacking and weigh your backpack and see if you can, head out with the minimum number of kilograms on your back. I made a little spreadsheet and wondered why it was so hard to edit. You can see that I had organized things under titles, backpacks, clothes, and so forth, and I just noticed that it was kind of awkward, because adding a row to the middle of a spreadsheet in Google Sheets is a little bit awkward. You have to right-click and find the right option. And I stopped. And I thought, I'll bet if it's this hard, I'm spreadsheeting wrong. And I thought about when I was using Pandas data frames a few years ago, when Amazon delivered a sales report to me for my friend's books in this kind of format, and it was horrible, because a Pandas data frame wants, on each row, all of the information about an item. It doesn't want the category backpacks to be orphaned several rows up from an actual backpack. And I realized that I was doing to myself and to this poor Google Sheet the exact thing that Amazon had been doing to its customers that needed sales reports. And so I was able to take the pattern that I first learned correctly for the first time in a Pandas data frame and apply it to my Google Sheet. I suddenly realized why it's so hard to add a row to the middle of a spreadsheet. It's because you never, ever, ever do that. Because you don't care about the order when you've set the data up correctly. Ever notice that sorting is so easy in a spreadsheet? Going back one slide, you would never, ever want to sort this spreadsheet. It would ruin it, because all of a sudden the backpacks would be mixed in with all of the other kinds of items in alphabetical order. Instantly, the first moment that you tried sorting something by grams or by name, you would orphan items from their category. Once you realize how you're supposed to have been spreadsheeting all of this time, you can now sort by grams, category, name, whenever you want, and because you're constantly sorting and resorting to bring different information to the top, you can always just add new rows right to the bottom, which spreadsheets make very easy. And so it was this moment where I got a pattern from Pandas data frames and realized that's how I was supposed to have been using spreadsheets all of this time, by making each row standalone, orthogonal, and meaningful, regardless of its order. I have talked before, even here at Pycon Ireland, about pipes and the way that data pipelines are a significant pattern and way to solve problems. If you haven't ever looked at it, take a look at McElroy's paper responding to an article in which Donald Knuth had written a many-page program in order to count the number of words, the number of times each word appears in a document. And McElroy said, well, that was all very clever, but I can do it in 6 lines of Unix shell script and have a hope of understanding the code the next day. I had long been familiar with that pattern. Pipes, the ability to get this data interchange format to put together smaller operations. It had not until late last year occurred to me that the clipboard, the cut and paste buffer in my operating system, well, my windowing system, is the same kind of generic data container, and in the same way that the element, the programmer running in a Unix pipeline can do a transform, it occurred to me to start writing transforms that pull data out of my cut and paste buffer and put something back. So let's see if this works. Used to, I would have to put in plugins to Gmail to do special things, but I now have bound to a hotkey here on my computer transforms that apply to any app I'm in. As long as I can get data by hitting copy into the clipboard, I can, for example, at work we have a lot of issues and diffs that we need to link to. This is what a diff identifier looks like. Usually if I'm sending an email, I want it to be an actual link so the person can visit it. So I hit copy, and my transform that I wrote recognizes this pattern and puts back in my cut and paste buffer for me a link. So if I see that someone has mentioned an issue, copy, transform, paste, and without any thought or work, I now have a working link to it. It used to take me 20 or 30 seconds each time to do the manual edit to create that link. I taught it to understand if the copy and paste buffer has $signs around it. Copy, transform, if the internet is working here, yes, then it understands, oh, that looks like a LaTeX formula. Let's turn it into an image and put the image in the cut and paste buffer so that I can now, should I, the next time that I need to mention the quadratic formula in an email message, I'll just type in the formula, copy, transform, paste, and get it right in that email. And what am I always wanting to do? I'm always wanting to write emails in Markdown rather than having to use Google's special little keystrokes in order to get formatting accomplished. It is also recognized by my magical little transformer, cut, transform, paste, and I now, not only in Gmail, in any app I'm in, I can just write Markdown, highlight, copy, and paste back in the formatted text instead. That is an application to my clipboard copy and paste buffer, a pattern I already knew from pipelines that it had not occurred to me to apply. So the application of patterns is often not immediately obvious. It can be years before you realize a pattern you've been using one place can be used somewhere else. Patterns are very, very popular in the way we structure code, the way we solve problems, because they're fast, they get us places quickly, and our lives, problem solving, would be slow and halting if we always had to invent solutions from the ground up. But there are moments when pattern doesn't work, when you don't have a ready-made solution or approach to a problem you're facing. I'm going to use the informal word search for the kind of exploration you do when you don't have a pattern ready and have to come up with something that, to you at least, is new. I'm going to work out a very small example just to get a picture of this on the screen. You want to send a string of characters to someone. How does the receiver know when you're done? Characters are arriving. How do they know when you've finished sending? There are several options, and you have to evaluate trade-offs as you think through the different approaches you could use to decide which one. One is that you could close the channel. Used to be modems had a line coming from the modem to your computer, if your hardware let you access it, called the data carrier detect, that if it went low, or high, I can't remember which, it meant that you had lost carrier. You weren't connected to the other end anymore. HTTP, the first version, 0.9, the way that you finished sending the web page was by closing the socket. How do I know if there's more web page still coming? Well, you waited till the connection closed. That's such an important thing to be able to do that sockets even support the ability to, as you're transmitting, shut down your end of the socket while leaving the other direction open for a reply, but so that you can still have the other end get that loss of signal, that inability to read, and so that they at least know that you're finished, even if they might want to say something back. Now, all of those approaches have a big problem. There are other reasons that you can lose the connection besides the web page being done, and that was a huge design flaw with HTTP 0.9, is that you could get half the web page and then the other server could go down. But your web browser would think it had received the entire web page because the connection closed. So where we really use this is we make heavy use of end of file for delimiting the end of our data on the file system. This isn't reliable in telecommunications or networking, but it is dead reliable when used with files. Think of it. When you write a .py file, there's not some special character you add to the end to tell Python, I'm done. Stop reading here. This is the bottom of the file. End of file is so reliable because it's not being done over a connection that could be lost, or if the connection to the hard drive is lost, your OS will be able to definitely give you an error, that we routinely use end of file as the way to delimit code, binaries, and everything else that we produce. We don't bother usually having an this is the end marker. We just trust that the end of file will tell Python where the bottom of the code is. If you don't want to use the medium itself to cut off the communication, which, among other things, means you can't keep using the medium for anything else if you hang up the socket, you're going to have to somehow, inside of the data, while the data stream is still going, mark the end. One is that you can agree that you're just sending ahead of time a fixed length item. The next thing I'm sending is a float. It's going to be 8 bytes, so the receiver can read 8 bytes and then know they're at the start of the next thing I'm sending. This isn't so good with things like text. Remember the days when they said, oh, the name field is 20 characters because no one would have a name longer than 20 characters, said, the Americans who hadn't met many people. The limitations that this kind of a fixed length approach imposed on text were always a problem, but this is heavily used today in, say, RPC protocols when you're using a data type that inherently has a built-in length. If you want to be able to handle things, text field documents of various lengths, you're going to have to do something else. One thing you can do is delimit it. Use a character or pattern that says it's done, that you put at the end of it. If the data that you're sending has an inherently limited alphabet, but the channel can handle a much larger one, then it's clear sailing. You just literally include all of the characters you want to send, and they are delimited by following them with something that could not possibly be part of the string. Here's an HTTP header. How do I know where the name of the header ends? Cleverly, they made colon an invalid character in HTTP header names. If you desperately needed a header with a colon in it, sorry, you can't have one. That means that I know when I reach a colon that I'm done with the name of the header, absolutely can stop right there. How do I know when I'm done with the entire value of the header, name, and value? Because, with the recent update of the standard, carriage return line feed cannot be part of the value, cannot be part of the text of a raw HTTP header, and so I know when I reach it that I'm done. I can stop reading. So if you are transmitting data that has a limited alphabet and your channel can express extra things, you can just use something outside the alphabet to say I'm done. The ASCII code that we use to transmit information, you've probably delimited things, line endings and data, with carriage return line feed tab, but knowing that delimiting information is such a crucial task in computing, the people who invented ASCII, as they wrote up those 32 control codes, a quarter of the entire ASCII character set is control codes. They gave you more than a half dozen other ways to delimit information so that you would never run out of delimiters that you could use that wouldn't collide with characters in the text itself. Start of header, start of text, end of transmission, end of medium, and then file, group, record, and unit separator are additional levels of delimitation that you can use to make sure that you cut up your text into usable pieces. Those poor characters, they're like the 32 most fundamental, and we never use them. I once would always in projects try to use at least one of them, so they felt like they were still being used. Bash, famously, when you put a $sign in a variable name, doesn't require you to have a set delimiter at the end because it kind of figures that the variable name ends with the first character that shouldn't be in a variable name, like a space. In case you do need to run your variable into a literal character like S, that could potentially be the name, a part of the name of a variable, it has an alternate way. You can use curly braces to force an invalid character, closing curly brace, to follow the name of your variable, because Bash needs to know where that name ends. I used to go to summer camp. They would always announce for safety at the beginning of the camp, if there is a fire, one of the cabins catches fire or has smoke, we'll ring this big camp bell and everyone should assemble in the gym. Someone would always put their hand up. But what if it's the gym that's on fire? They never had an answer. What if the gem is on fire? What if you want to use a delimiter, but sometimes strings will themselves need to contain that delimiter because it's a useful character? In that case, there's two things you can do. One is we have some encodings that people have worked out that regardless of whether a character would be valid or would be confusable with the delimiter, get all characters alike and mix them down into a smaller character set that is guaranteed to not look like a delimiter. Base 64, which is built into Python, is one such example. But what you're probably far more used to seeing, because encoding often makes strings completely unreadable to humans, is escaping, where we decide to give a pass to the characters that don't look like the delimiter. So you start with a single quote, you're looking, end of the string will have a single quote. We tell characters, well, if you're not a single quote, you can just appear literally. This makes the string very readable. But what if you wanted a single quote in that string? And different programming languages have come up with different systems of escaping, either doubling the character or introducing a second special character with a number of complexities that follow in order to allow that single quote to be part of your string. I note that traditionally in English typesetting, we've had the problem that the period can mean many different things. You would think that a period would mean I'm delimiting the end of a sentence, but we also use periods for abbreviations, acronyms, and of course a century or two ago, periods were far more common before we started leaving them out of most acronyms, for example. This is the edition of Pride and Prejudice from the mid-1800s. Notice that they use white space after a terminal period that ends a sentence so that your eye can very easily pick out that it's doing different duty than the periods that, for example, sit at the end of an abbreviation. In this case, visual presentation is being used to disambiguate a punctuation being used as a delimiter from punctuation that's merely signaling something else. If escaping, somehow making delimiters look different from the same character serving as a non-delimiter, if that doesn't work out for you, there's a final approach, which is reliable, efficient, and used in a lot of different formats. Just prefix the value with the length. We normally associate this with protobufs and binary on the wire formats. It's the way TCP packets work. You have a fixed length field that tells you the length of the rest of the packet, but it used to be used in programming languages. In Fortran 66, you could put some digits, the capital letter H, and you told Fortran, I'm about to type, in this case, 11 characters that are a string. Doesn't matter how crazy the characters are, they would be read in as a string because they needed no closing delimiter, because Fortran simply counted to 11 to get them all in. Problem. How do you know when you're done with the length? What do you do if it's the gym that's on fire? It turns out if you take that very last best option from among the choices, best in the sense that you get to just transmit the data literally with no special characters whatsoever, you get to go back the beginning of the design and play the game all over again, because how do you know how big the length is? And you get to make any of those choices you want to express the length. HTTP is an interesting example because even though the payload it sends, the web page or binary image, is sent usually completely unescaped as a raw block of data on the socket, the web browser knows how far to read before its end through a textual length field that's delimited by a carriage return line feed. So you read the content length as a variable length decimal string that then tells you how big your block of binary data is. Again, because they wanted to length prefix their data, they had to go play the whole game over again, and in this case chose text delimitation as the way that you'd know when you were done reading the content length. So that is an example of, in this case, a design space, a search you might do, thinking of different solutions to a problem. If you're encountering that realm and that design space for the first time. I'm now going to step back and consider it in the abstract, what it is like to tackle a problem big enough and complicated enough that you have to try several things out and take different directions to get something accomplished. Again, I'm calling that, informally, for the purposes of this talk, calling it search. When you don't have a ready-made pattern, you have to step back and undertake a longer process in order to put together an approach. I really first saw this modeled effectively when I took my physics class at Georgia Tech. I had avoided taking physics my first year. It looked miserable. Huge lecture hall, 150 people, multiple choice tests. You never got to talk to the professor. It was all TAs. And my friend kind of laughed, who was a physics student, and said, well, why don't you take the real one? And I said, the real one? And he said, well, you don't think physics students sit in a lecture hall with 150 people to learn their discipline. And he let me in on a secret. The physicists had their own physics classes where you sat with 15 people in a small classroom with a chalkboard and talked with the professor about the solution he was putting together in front of you. And there was no sign-up requirement. Many majors, if they had a better version of the standard curriculum class, had to protect it with all of these qualifications or interviews with the professor. But apparently almost no one wants to take the more advanced physics class, so there were no protections in front of it whatsoever. I logged right onto the system, was able to sign up for it, and found myself in a small classroom with a professor we all interacted with and asked questions of, and Dr. Wiesenfeld did an incredible job of setting up a problem on the board, trying to get into it, trying to set up some equations that would let him in, and running into a dead end. That hadn't happened in high school when they tried to do problems. He would back up, try a different way in. And it wasn't always the second or third way that would work. Sometimes you would realize that the algebra of the first way was probably easier to push through, but you had to try different ways in to see. I don't know how much of what he did was scripted and how much was just letting himself hit these problems afresh each year in front of us undergrads, but it was incredibly effective in letting me begin to get a feel for what it was like to have to go in at a problem several times in several different ways to do search and to learn the landscape around it. The result was always a relationship. After all the simplifications had taken place, we finally could state the relationship against the different parts of the problem. I remember partway through that year talking to a friend who had just taken the normal physics, and I looked at one of his tests he'd gotten back, and I said, that's not physics, there's numbers in it. Like the answers were ridiculous things, like 7.5 meters per second. What does that tell you about the universe? In this class, we always got out a relationship that let us then step back and say, so what's more important? The angle I set the cannon at, or the amount of powder I put in? If I can tweak one of those, which do I want to tweak? And you could go through the different parts of the expression. I got to take a loudspeaker design class from the renowned acoustic designer, Dr. Eugene Patronus. Oh, by the way, this, my friends who were actual physicists and went on told me you never actually do this in real physics. The little dx's and dy's and all of that simplification of the algebra we did in particle dynamics never happens. Like they take you to the second or third year, they have this big laugh and say they just did that to teach you problem solving. Apparently real physicists use something developed here in Dublin at Trinity College called the Hamiltonian. That's how Rockstar physicists solve problems. But it's not what they teach freshmen. They send you back through the Newton and Leibniz kind of approach. And from Dr. Eugene Patronus, taking his acoustics class, when he pushes through, and it took several chalkboards, the equations of motion of a sinusoidally excited loudspeaker, the resulting equation is more complicated looking than equations I was used to dealing with, but he then patiently took us through each parameter, and with an equation, if that's what your problem leaves you with, you get to ask, okay, what does the elasticity of the microphone, what effect does it have? The size of the box you put it in, what effect does that have? And you see, oh, a loudspeaker is only going to be useful over a limited range of frequencies. That's why you need a bass and a tweeter separately. You get real understanding of the physical world by having, when you're done, this equation that tells you how the different parts of the world fit together. But I noticed something. Having taken General Physics 1, having seen someone model going in at a problem and sometimes failing and having to try from a different direction, having been sent in against some problems myself that sometimes I found the solution for before the test had to be turned in, sometimes not, I found that I then did pretty well in a series of later courses that most students despised. Your grade is on the line. You need to turn that homework in. You need to get that test finished. And remember, in the American system, you have a lot of your family's fortune or your own future personal fortune on the line to have you at this university. You do not want the question, the open question of whether you'll get through a search space in time for the test to be turned in to control whether you get a good grade. There was a lot of misery and panic that I observed in those classes that really got you into problem spaces that require search. Because search is emotionally difficult. You don't know when it will finish. You don't know when you'll get done. You don't know when you're doing the right thing until you finally arrived at a solution. And I found that having taken that physics class really prepared me for all kinds of problem solving, because I knew how to kind of handle myself emotionally if I had to take a long, long try at a problem where I might not know when I would finish. My friends that were engineers, I never took differential equations, they said that differential equations is that in spades. Derivatives, often a very pattern-based. Oh, I recognize this one, get the derivative done. Integrals are a little more open-ended, take a lot more finesse, especially with two-dimensional integrals to find a tractable way to approach it. They told me differential equations are just crazy, which are, of course, the way the universe actually operates. The famous mathematician and educator, George Poya, once, when teaching a particularly difficult differential equation, said this: in order to solve this differential equation, you look at it till a solution occurs to you. Differential equations are so difficult that often you can take some steps to explore the mathematical space around them. You can make some tries at a solution, but it's going to be a week later as you're walking somewhere or waking up or in the shower that you're suddenly going to get the answer. It's something difficult to build a course around, because how do you control inspiration in a classroom setting? That's why most of our education is pattern-based. If they give you patterns, then even if you're one of the children that takes a while to get subtraction, you at least can be doing the mechanics of it successfully and getting good grades before the concept itself kicks in. The kind of learning that really involves inspiration and creativity is very difficult to do at the regimented pace that modern classrooms require. So there's pattern, there's search. What happens when search fails? What is the word for that? Here, I'm going to defer to Robert M. Persick's famous book from, I believe, the early 1970s, Zen and the Art of Motorcycle Maintenance. My grandfather, who was a physicist, believed this book to be the best description of science he had ever read. It's interesting, the things that get handed down to us by our ancestors that came before us. Let's see, yeah, this is, almost shows up on the projector. What I inherited from him was books and a little connection that I made. He died in the 1990s. A little connection that I like, that I maintain with him, is that he wrote his own indexes to books. As he was reading a book, when he got to significant passages that he knew he'd want to go reread later, in the front or back flyleaf, he would note down the page number and a notation to remind him of what passage that was. So his library of books had his own little indexes to get to the parts of the book he thought were important. And here I will quote from the first passage that he listed, there in the upper left, the famous passage in Zen and the Art of Motorcycle Maintenance on stuck. He describes attempting to do maintenance on your own motorcycle. You're not gonna take it to a mechanic. You're going to fix it and improve it yourself. I know, which a lot of motorcycle people do. And you're working on a piece and you break it. And suddenly you have no way to get it out. He describes the emotions you go through at that moment of realization as follows. This isn't a rare scene in science or technology. This is the commonest scene of all. Just plain stuck. In traditional maintenance, this is the worst of all moments, so bad that you have avoided even thinking about it before you come to it. This is the zero moment of consciousness. Stuck, no answer, honked, kaput. It's a miserable experience emotionally. You're losing time, you're incompetent, you don't know what you're doing, you should be ashamed of yourself, you should take the machine to a real mechanic who knows how to figure these things out. I will not ask you to raise your hands. I'll simply ask you, have you ever, when programming, felt a similar emotion? This is the concept of stuck. That's the word I'm going to use for potentially the misery that is out there beyond search. When the search fails, you're out of tricks and you don't even know what you're going to do next. I'm going to make the claim that a lot of being able to enjoy programming or any other hard problem-solving discipline is learning to emotionally manage the state of stuck. It's interesting to read Zen and the Art of Motorcycle Maintenance if you haven't, because, slight spoiler, his way of dealing with it emotionally is he came to believe that it was similar to the state that Zen Buddhist monks practice entering for years. Because he claims when you're stuck, you finally have absolutely no expectations about what's going to happen next. You are finally divested of your rational Western scientific pattern matching, I know what I'm doing this afternoon. You suddenly have no idea what you're going to be doing for the rest of the afternoon, and for a moment get to encounter reality raw and without any preconceptions. Whether or not that's your way of emotionally handling the state of stuck, saying, I'm stuck, I'm Zen. Dealing with it in one way or another is going to be an important part of problem solving. So I'm going to make the following claim, and so this is the central claim of my keynote here. Novices, which can mean someone learning Python for the first time, or it can mean me, having used Python for 20 years, learning a new API or library or programming approach for the first time. A novice, someone doing something for the first time, generate programs by pattern, otherwise called Stack Overflow. And once we begin to understand the problem space, maybe our own little searches out into the possibilities. But once something goes wrong, we start debugging from the default state of stuck. Because I'm going, as I put a solution together in code, I'm going to pull from small things that I know and understand. The universe is going to pull the bug I run into from the complete and total set of sources of all bugs that might be things I understand or might not. Why does a bug perhaps instantly move me to stuck? Because anything could have gone wrong. Nothing constrains the error to be in part of the system that I understand. For example, how often have you ever been sidetracked by what turns out to be a problem outside of your code itself? You're staring at your code. I'm changing this. I think I just fixed that. I changed the plus to a minus. Why isn't it fixed? Again, I won't ask for a show of hands, but have you ever realized 20 minutes later that you've been saving this entire time to the wrong file? Or in the wrong copy, right file name, but wrong copy of the repository. Or right repository, but you're logged into the wrong server. Maybe you're logged into production. Whoops. Oh, or you're making the correct edit, or at least an edit that would change the behavior, but you need to stop and restart the program and didn't realize that. You're hitting reload in your browser, it's the wrong URL. Oh, this hit me yesterday. The traceback actually named another line of code, and I, thinking I know what the error was, went to the same line of code 4 lines up, which doesn't have a problem, and which I can look for a problem on for 10 minutes without fixing the actual bug. Have you ever written a module whose name is the same as a standard library module? How long did that leave you hung up? Oh, I see someone who did. When a novice makes an error in Python, and this happens in the only thing I can think of that doesn't involve this danger is an extremely constrained learning environment like the Scratch language from MIT, which you should take a look at if you know any kids or beginning programmers who want an environment where naming a module after a standard library module they didn't even know existed isn't a danger. But if you're using a full-powered programming language to try to learn to program, errors can come from anywhere. They can involve things that you don't even think to look at, don't even think to check. You've used an editor for a week. It's your first week. You didn't know you could save to the wrong directory and that it would create a PY file there, but not where you needed it to. And this is where we run into the fact that we often want people to be happy and delighted as they're learning programming for the first time, and we don't realize the extent to which solving real problems in programming often requires the full-bore scientific method, stepping back from your incessant editing of the code and asking, could there be something bigger that's wrong here? Are all of my assumptions about the file I'm editing, the version of the library I'm using, my operating system, are all of those assumptions really correct? And that a lot of people even get through university without heavy, hard, difficult training in how to step back and question assumptions. Robert Pirsig says in the same book that the real purpose of the scientific method is to make sure nature hasn't misled you into thinking you know something you actually don't know. The universe is always encouraging us to make assumptions, because unless we make quite a number, we can't concentrate on just one piece of code and move forward with it. But there's such a danger to doing that, because any of our assumptions, even the ones that aren't in our heads at the moment, could be the one that goes wrong. Novices, by their nature, I'm claiming, because there are so many assumptions they don't even know they're making, novices get stuck. That's almost their default place to arrive at when the pattern doesn't work, because they don't know yet the tools they would need to search for a solution. So if I'm correct that novices tend to get stuck, notice there's a corollary. The default emotions of computer programming are hope and misery. If you're starting out, again, as a new programmer or an experienced programmer with a new tool, you will switch back and forth between opposite ends of the spectrum. Remember that the famous the book that kicked off test-driven development at the beginning of the 2000s begins by stating test-driven development is a way of managing fear during programming. People today list that there are a number of benefits, additional benefits to the approach, but its author thought that the emotional benefit, the defense against fear by taking small steps followed by small victories, was its primary purpose. So how can we support novice programmers? I didn't want to end without at least the beginnings of a few suggestions, having outlined this problem, so I'll just mention a few. When I'm teaching people new approaches, I encourage just writing one line of code at a time, then a print statement, or looking at it in a debugger to see what it did. Never let them write 2 lines, because if something goes wrong, they won't know which line the error was in. Version control, frequent commits. You don't want to write a dozen lines of code, try changing something, suddenly having it break, and have lost the work you did to get 10 lines to a working state. Encourage people to call for backup until they have a robust set of debugging skills and know how to run LSOF and know how to run strace and know how to look at the interior state of Python. They're not even going to be able to do effective search, and calling you or another experienced programmer to their side when something goes wrong is a great chance for them to see modeled what I learned from Dr. Wiesenfeld, how another confused person, but with more experience, begins to move in towards a hard problem to try to get it solved. And then, I think very important, especially if you have more junior developers in your startup or in your company, when you're doing work in your startup, in your hobby, in your company, learn to try writing things twice. We have bad habits as programmers. Fred Brooks famously said, when you write a version of a library or system, plan to throw one away. You will anyhow. He famously said that the first one you write won't be very good. You'll always be needing to rewrite it. I'll note that that's actually often backwards for me. For me, it's not always the first version of something that goes wrong. I often write a big complicated routine, finally get it working, and then I think, I could have done that more simply. I always immediately commit to version control. Don't throw that first version away. Create a branch, commit to version control, back up, and I'm like, I'm going to do this better. I spend a half hour writing a more elegant solution, and right as I'm finishing, I realize that it doesn't handle that special case that I'd forgotten about. That's why I made the first version of it so hairy. And so I throw the second one away. Very often, if I try several approaches, I could do this with a dictionary. No, the first way was better, but it's only by doing a few different approaches that I find one that's really readable, sometimes the first or second or even the third. Back at Django Con 2014, I made the following claims. That once my code is finally working, I've been working and finally the routine works, it's probably better described as barely working, right? Because I'm just at the moment of having crested the boundary between broken code and barely working code. What are the chances that I've finally crested that boundary at the point where my code is the most readable, elegant, maintainable, and best factored? So the mantra that I sort of taught in that talk is, once new code finally works, I'm probably about halfway done. I find that if it takes me an hour to write up in code a function and some simple tests, I need to commit to version control while it's working, save the moment, then probably spend another hour doing more documentation, trying a few new tests, and rewriting parts of it to have any chance of it being readable or maintainable when I then am rereading it several months later. George Poja, who I mentioned earlier, the Hungarian, we got so many good Hungarians thanks to the Second World War. It was really, really an incredible number of Hungarians on the market. And the Manhattan Project, largely staffed by Hungarians, atomic physics, I believe universities here and in England got a number of very great thinkers. Poja, I believe, was at Stanford starting in 1940 and for the rest of his career. He was especially renowned not only for his work in math, but for the thinking he did about problem solving and the brilliance he had as a teacher and the way he packaged that in a famous book called How to Solve It, in which he talks about teaching students what I've called search, teaching students how to try to find a way into the problem, how to back up when they've made a mistake, how to look at a problem that they think is too big for them and start putting things together they don't even see at first that will eventually form a solution. And I'll end here with a quote or two from him. He said, even fairly good students, when they have obtained the solution of the problem and written down neatly the argument, shut their books and look for something else. Poja couldn't believe it. Doing so, they miss an important and instructive phase of the work. To Poja, some of the most valuable work you do on a problem is after you've generated the first solution, as you then go back to see what other things are illuminated by that solution, and by the ways you missed that would have been easier paths in towards that solution now that you have it. He thought a lot of problem solving happens after you first solved the problem. Encourage novice programmers to explore on past the first solution they happen to come to. Why? Because that teaches them the beginning phases of search, of doing something a second and a third way, which, if they can develop that skill, is going to be their defense against stuck. Poja said this, your problem may be modest, but if it challenges your curiosity and brings into play your inventive faculties, and if you solve it by your own means, you may experience the tension and enjoy the triumph of discovery. Try in others that you're teaching and in yourself to train up and strengthen search. Because when pattern fails and that Stack Overflow answer doesn't quite work for you, it is your defense. Search is your defense against stuck. Thank you very much.